Hello and welcome to this presentation about a toolbox for mechanized first-order logic, which is joint work with Johannes Hoster and Mark. I will start with the presentation and you will get to know Johannes and Mark later as well. So I want to start with this bad example from the paper we have presented on Wednesday at ITP about the mechanization of incompleteness in first-order logic. And here in this example, you see a couple of the problems you have to deal with when you work with a deeply embedded object logic in Koch. So first, formulas, even if they are under context, are not really helpful because they can be cluttered with variable indices and substitutions. So it's not clear what is exactly going on here. And the goal itself is also unreadable, and it's not in Koch's logic, but by the turnstile here, you see that it is in a deeply embedded deduction calculus. So you have to use the rules of the deduction calculus as well, with not much support. And this is why the proof does not look that straightforward, and it was not fun doing it in Koch. So to give you a bit of context, we have been synthesizing a library of first-order logic from a couple of mechanizations we have discussed at mechanization conferences. And the results are mostly concerned with completeness, incompleteness, and undecidability. And in fact, the big chunks of the library are part of the Koch library of undecidability proofs. And since we are mostly interested in these meta-theoretic results so far, when we want to represent first-order logic for these purposes, there's no way around a deep embedding. And one standard way of doing a deep embedding is to use the Brown encoding of the syntax with parallel substitution. For the model theoretic semantics, you use an embedding into Koch's logic, and the deduction systems are represented by inductive predicates. And while this is all well understood and behaves nicely when you want to do meta-theoretic structural results like weakening or soundness, if you want to do concrete results as the one I have shown you before, it's a bit more annoying because writing down the formulas is not fun because you have to chase the Brown indices. Even when you would do semantic derivations that compile into Koch statements, still first-order syntax might be exposed. And if you do deductions in the deduction system by hand, then there is no support. And this is all not easy to handle for someone who would use this library without having developed it. So there should be solutions for this. And one way to tackle these problems is to come up with compromises. For example, Olivier Laurent presented at this year's CPP that the syntax can be represented such that you still have names, which is easy to work with, but still can prove structural properties easily. Or you just do an overall two-level approach, which is what we do. So for each of the three problems, we implement a tool that helps solving this problem. And I want to now, in a quick demo, show you the first tool that we developed. Okay, so I first introduced the running example we use in this talk, which is the commutativity of addition. And you have probably seen the proof over Koch's natural numbers at some point in your life. And it's not that hard. You do an induction on one of the numbers. In the base case, you just have to rewrite with the lemma. And in the inductive case, you rewrite with the inductive hypothesis and the lemma, and then you're done. Okay, so this proof is straightforward. And the hope is if you do this in first-order logic, for example, over an axiomatization of Peano arithmetic, the proof doesn't look too different. So first, this starts with the statement itself. So we import Peano arithmetic. And now writing down the statement in the concrete syntax is actually not too hard because you just have two outer binders. And then you can, by the Brown indices, refer to the correct binders. So here we need variable 1 because we jump over one binder and then we have exactly written down the same formula. So I can guarantee that as soon as you have nested quantifiers, this becomes really unfeasible because then you have to calculate in your head which variable refers to which binder. And this is why we implemented a higher order abstract syntax input language, where you use the Koch binding machinery to represent binders. So you don't have to count indices, but you just write down a Koch name, use it later, as you are used to it from working with Koch. So I import this Horst package, overwrite the notations, and now I can write down the same statements, so commutativity of addition, but now I can quantify and just introduce two new names, use them in the body as expected, and indeed under the hood, this is compiled down to exactly the same, the Brown formula we have seen before. All right, so this is the first tool, and now Johannes will present the second tool.
Okay, thank you, Dominik. Hello, everyone, to my part of the presentation. And we're now talking about the context of semantic derivation. By this, basically, we mean that we're working within a model. In this example, we're working within a model of piano arithmetic. And now we want to prove that in this model, addition is commutative, which is this first order formula here. And now basically, this just reduces to a Koch formula, which is the nice thing about semantic derivations, which we can now prove with normal Koch tactics. So we can just do intros here, for example. We end up with this. And now at this point, we would like to do an induction. However, the induction axiom in piano arithmetic first order is a bit interesting because it's actually an axiom scheme. There are infinitely many induction axioms, one for each possible first order formula you would want to do an induction over. So if you now want to apply the induction axiom, we need to actually show that the statement we're doing induction over actually is representable in first order logic. And formally, this means that there exists some first order formula and an environment such that if we interpret our formula in this environment, then it's equivalent to like the original Koch formula, which we wanted to do the induction over. Okay, so now in this case, it's rather straightforward to find this first order formula. And it's also, in this case, relatively straightforward to find this environment. And basically, this environment now needs to contain this B here, because this B occurs freely in the statement we're doing induction over. So we need to put it in the environment like this here. And we need to make sure that like the index where it's at in the environment matches up with the Brown indices of this variable B here, which you can see here. So now that we have done all of this, we can now show that this is equivalent to the original statement we wanted to do an induction over. And this can just be done by reflexivity in this case. Okay, now you have seen all of this. And you might also guess that this is really tedious to do every time you do an induction, especially when there are more free variables and so on. And so we have just developed a simple single tactic, which is just called represent and which can do all of this automatically. Okay, now that we have shown that we can actually apply the induction axiom in this case, we need to do the actual induction. So we need to show the base case and we need to show the induction step, but these can just be shown by a modest amount of rewriting. Okay, and this concludes our proof in this case. And now let's talk a bit about the theory behind this. And what we have done here is basically a process called reification. And by reification, we mean that we take something from the meta level, in this case Koch formulas, and we extract them into an object we can work with in Koch. And so what we're doing here in this context is we're extracting Koch formulas into our first order abstract syntax, but reification in general means taking something from the meta level into the object level. Okay, and the way reification works, at least in our case, is that you just recursively look at the Koch AST and try to figure out, for example, is this a quantifier? And if this is a quantifier, you then recurse down into the formula that's quantified over. And then in the end, you get a Koch formula for your complete, you get a first order formula for your complete Koch formula. And also what we do is, as you may have seen, we have to construct these environments of the three variables. And we just basically do a first pass where we construct the environment. And then in the second pass, we recurse the Koch AST again in order to find the first order representation of it. Okay, and the way we do this, it's implemented in MetaKoch for various reasons. The first and most important reason is that we already had experience with MetaKoch, which is why we chose it. And also in MetaKoch, you can do a deep introspection of the actual Koch AST. And this is important for a particular reason we will talk about later. Okay, but none of this is really new. Reification with MetaKoch has already been seen, for example, in Hoster and Kunze. And also a member of our group previously worked on reification of first order logic. And he worked with type classes, and some things didn't work out the way he hoped. He recommended that the next time someone does this, one should do this in MetaKoch, because perhaps some things might be simpler to implement there. Okay, and the main difficulties in this case are that we have to basically keep track of binders. It's not enough to just look at the S structure. You also have to figure out which binders bind which variables and properly lift this into the first order abstract syntax. And also building the environments requires a different path, which is orthogonal to the actual reification. Okay, so now you have seen that this works. Now let's talk a bit about the issues there still are with this. And first of all, finding the proofs that the actual first order formula you found is equivalent to the original Koch formula you wanted to find it for is rather slow. And we're not really sure why, because in theory it should works the same as finding this actual formula, but somehow constructing this proof that the formula you found is equivalent to the original formula is slow, and we're not really sure why. We tried looking into profiling MetaCoch, but we really didn't know how you might want to do this. Okay, and also reification in general, it just looks at the AST and the syntax. So it doesn't look behind definitions, which means that if you define something in order to hide like your formula behind it, then the reification engine at this point would fail because it doesn't unfold this definition. It just sees that there is a definition it doesn't know about, then it fails. So basically what you have to do instead is mostly use notations instead of definitions. But however, this is not that large of an issue in practice for us because most of the existing proofs already use quite a large amount of notations. And the engine was basically written such that it works with the existing developments, which already rely on notations quite heavily. Okay, and finally, our reification engine only knows about like the basic things of Koch, which can easily be lifted into first order logic. So for example, we can reify quantifiers, and for example, implication and so on. However, something like equality, it can currently not be reified because equality does not exist in our first order formulation, because not all first order theories actually have a native quality, so to speak. So if you have a formula with equality and you try to reify it, you just get the same error you would get when you reify any definition you don't know about. However, there is a potential solution for this, and this is basically called extension points, and this is also what we did in the demo. And by an extension point, we basically mean a user-defined type class instance where the user then can define additional handlers for things the reification framework does not know about, like extensional equality, and this is what we did in the demo. However, at the moment, writing them is rather tedious. Okay, so this concludes my part of the presentation, and I will now hand over to Mark.
The third tool we want to show you is concerned with making deductive proofs easier. Dominik already mentioned that there are quite a few challenges associated with deductively verifying formulas, in particular related to the De Bruijn encoding. And he also already briefly showed you this real-world example, but maybe I can point out a few highlights here. For instance, notice how at multiple places in this proof you need to explicitly change how the goal looks like. And the reason for why you need to do this is directly related to the use of the De Bruijn encoding and the substitutions. But this is also only the tip of the iceberg. Generally, doing deductions with De Bruijn indices leads to lots of overhead because there's a ton of bookkeeping that you always need to do. And then even this proof here already heavily relies on custom tactics that are used to make things maybe a bit more bearable. But nonetheless, like Dominik said, proving this is not a nice experience. You've already seen how the goal looks like at one point in this proof, and I think you can imagine that keeping track of all of this is a challenge. The tool we developed to address those issues is largely inspired by the Iris proof mod, because one nice feature of the Iris proof mod is that I have this custom goal view where hypotheses get names and are printed one below the other like we're used to from Koch. And this is, of course, way better than having your context just represented as a list of formulas like it is here. And then they also have custom tactics that allow for reasoning that's a bit more high level than just applying individual deduction rules, which is also something we'd like to have. Unfortunately, in our setting here, using the Iris proof mod would not work because it's geared towards shellily embedded logics. So the Iris proof mod doesn't work with the De Bruijn indices. Therefore, we wanted to develop our own proof mod with a similar look and feel than the Iris one, but for our deeply embedded logic that then also addresses the issues we have with the De Bruijn indices. One of the main selling points is basically that by using our proof mode, you can do deductive proofs without needing to interact with the De Bruijn indices or substitutions in any way. And to show you how this looks like, we have another demo. So we once again have the example of commutativity of addition, which we can now nicely write down thanks to our input language. But as you can see, as soon as we start the proof, the De Bruijn indices are back. But by activating our proof mode using the tactic fstart, you can see that the goal immediately changes and the De Bruijn indices are replaced with named binders. Also, the context is now displayed above this line, just like in the iris proof mode. Of course, when we want to prove commutativity, we need to do an induction. And we can do this by using our custom f-apply tactic to apply the correct instantiation of the induction axiom scheme of PA, which produces two subgoals. In the first case, we can introduce the variable x using our custom f-intros tactic, which leaves us with proving that 0 plus x is the same as x plus 0. Earlier in this file, I already proved the lemma that says that for all x, x plus 0 is equal to x. So we can rewrite using this lemma. And then what's left here is simply an instantiation of the zero addition axiom of PA, which you can again apply. Another nice feature here is that we don't actually need to provide this argument x here. So just like with the normal applied tactic in Koch, we can f-apply just with the name, and then the correct instantiation is found automatically. Then in the second case, we can again introduce, and notice how the inductive hypothesis pops up in the context with the name IH we specified here. And once again, we can rewrite using a lemma, rewrite with the inductive hypothesis, and finally apply the second addition axiom of PA, which finishes the goal. Notice how at no point in this proof we needed to interact or even look at the Brown indices substitutions in any way. So technically, the user wouldn't even need to know what the Brown encoding is or how it works, because all of it is hidden behind this abstraction. So when we now switch back to our earlier example, we can now compare this to the same proof done using our tool. And the first thing you should notice is that this results in a way more compact proof, and we would argue also in a way more readable proof script. And this also showcases some of the other features we built. For instance, introduction patterns passed as strings, which is also oftentimes very helpful. And at the same point in the proof, your goal no longer looks like this, but like this, which we feel is way more reasonable. On the technical side, our tool is almost entirely based on LTAG, except for a small metacode plugin that we use to turn strings into identifiers. And all of the custom goal view and name binders and so on are powered using Koch notations. In fact, we actually define aliases for our deduction type and for lists and variables and so on, and apply notations to those, because this way we can make sure that the notations are only active if our proof mode is active. And those aliases also carry the names of the hypotheses and variables. For instance, we have an alias for the const operation on lists, which takes a string as an extra argument, which then gets printed as the name of the hypothesis in the context. Among all of the high-level tactics we implemented, rewriting is probably the most involved one, because like Johannes mentioned before, equality is not built into our first logic in our setting, and instead the user can simply choose their own equality symbol from the signature, and then needs to prove certain congruent lemmas about it. And then the actual rewriting is done using the following rule. So you can see we rewrite by applying a substitution, which requires carefully setting up and transforming this formula such that the substitution ends up with the correct rewritten formula we wanted to. Although being a bit involved, we found rewriting to be one of the most useful tactics in allowing for more compact and also more elegant proof scripts. We actually benchmarked the tool on many other proofs from the same development as the example I showed you earlier, and we were able to reduce the proof script size by almost 50% on average, which we think is quite nice. But we also want to point out here that the tool is only a prototype, so there are certain limitations to it. For instance, we're at the moment we're most concerned with performance. For larger proofs, like the example I showed you earlier, there can be noticeable delays for tactic execution, and therefore there should be work put into making things a bit more efficient. And we also worked on supporting deduction on theories so that your context can be infinitely large, but this is not fully supported yet. And now I hand back over to Dominik.
Okay, so let me quickly wrap up. We have presented three tools: a higher order abstract syntax input language, a reification tactic, and a proof mode that help you using our first order logic library. Of course, I should say that all of these ideas have been on the market before, so we didn't reinvent the wheel, but we adapted the wheel to suit our library. And the prototypes we have implemented so far certainly have their limitations, so they are proofs of concepts. But still, you can already now use our first order logic library without caring about the implementation. So you can use the de Bruijn syntax without even knowing what de Bruijn encoding is. And also the tools are in principle adjustable to your logic you are working with, if it's kind of similar. So for example, if you work with modal logics or linear logic or propositional logic, and you are interested in using one of the tools, you can get in touch with us. You will find more information if you click on these links. If you have the slides, the links are also in the abstract. So there are more demos. There's actual manuals written about the tools. And for now, we want to thank you for your attention, and we're looking forward to taking your questions.